Example 3, we want to consider the parabola y is equals to x squared. Okay. Part 1, we want to find the equation of the tangent to the parabola at this particular point. Part 2, we want to then look at a line that passes through the focus, okay, which is also perpendicular to our tangent, and then we're going to look at the intersection point between my tangent and my random line, and we're going to check out some locus. So what we're going to do here, obviously start off with a diagram. Okay, let's say I've got y is equals to x squared. In this case, one thing that some people might pick up on is the parametric representation of the point P. Okay, P comma P squared. This is actually not of the standard form 2AP AP squared, right? If you try to find the value of A, it doesn't work. Okay, the reason for that is because we're using a different parametric representation. So if that's the case, the way in which we're going to find the equation of the tangent though is still exactly the same. We're going to start by considering the point P. Okay, so at the point P given by P comma P squared, the gradient of the curve, okay, which represents the gradient of the tangent at that particular point, is still given by dy dp over dx dp. If I differentiate p squared with respect to p, I'm going to get 2p. If I differentiate p with respect to p, I'm going to get 1. Okay, so therefore dy dx in this case is 2 times p. Once I've got my gradient of the tangent, for the tangent itself, okay, so for the tangent at p, I'm just going to get y minus y1 is equal to the gradient times x minus x1. If I expand the whole lot, I'm now looking at y minus p squared is equals to 2px minus 2p squared. And if I move the minus p squared from the left to the right, we're now going to end up with y is equals to 2px minus p squared. Now part 2, we want to look at a line that passes through the focus of the parabola, which is going to be perpendicular to the tangent. Now take note that just because I'm looking at a line which is perpendicular to the tangent doesn't mean that I'm looking at the normal. Okay, in this case, you guys can see that my resultant line in this case does not pass through P. I mean, the line that we're looking for does have gradient, which is the same as the gradient of the normal. Okay, but take note that this orange line over here is not the normal. So in order to find out the equation of this line, what I need to do is I need to find out where the focus is. Now, given that we're dealing with a parabola, y is equals to x squared. Now recall that normally speaking, our parabola is given by x squared equals to 4ay. So if x squared equals to 4ay, that implies that 4a in this case is equals to 1. So a is equals to a quarter. That means that the focus that we're looking at is therefore given by 0, 1 quarter. Now the gradient of the tangent in part 1 was given by 2p, okay, and for some reason I labeled this as part 2. Okay, so let me fix that. This is now part 1, right? We said that the gradient of the tangent is equals to 2p. What that means is that the gradient of this line that I'm looking for therefore needs to be negative 1 over 2p. Okay, because the two lines are perpendicular. So checking this out, let's say part 2, the gradient of the line I seek has gradient negative 1 over 2p. And I know that it passes through 0, 1 quarter. So therefore the equation is given by y minus y1 is equals to the gradient times x minus x1. So if I expand the whole lot, we're now looking at the equation y minus a quarter is equals to negative 1 on 2p times x. And if I move the minus 1 quarter from the left to the right, we're looking at y is equals to 1 quarter minus 1 on 2p times x. And when I look at this, if I want to put everything over the same fraction, okay, because the question wants us to show that the equation of this line is given by y is equals to p minus 2x over 4p, the common denominator which we're going to use is 4 times p. So the 1 quarter over here, I need to multiply the top and bottom by p, so I gain an extra p up at the top. For the 1 over 2p times x, I'm going to multiply the top and bottom by 2, okay, in order to get the 2x in the bottom. So I gain the minus 2 times x up at the top from the second fraction, and that's how we're going to get the equation of this line as y is equals to p minus 2x over 4p. Now, as soon as we have this, part 3 wants us to hence or otherwise find the locus of the foot of the perpendicular from the focus to the tangent. Okay, so I've come along, I've labeled this intersection point between the two lines as t, and we know that p is a variable point on the parabola, right? So obviously as p moves around on the parabola, okay, the tangent changes. So if the tangent changes, then my orange line, which is the perpendicular line to the tangent, which passes through the focus, is obviously going to shift as well. And as a result, the point T will obviously change according to P. So what I want to do is I want to find out, as P changes, how does T change? So the first thing that we have to do is find the coordinates of T, right? T is just the intersection point between my tangent and my orange line. So therefore, to start, right, what I'm going to take note of, part 3, is my orange line is given by y is equals to P minus 2x over 4P. And my tangent is given by y is equals to 2px minus p squared. So if I solve simultaneously for T, right, so solving for T, what I'm going to get is equating the two. I've got p minus 2x over 4p is equals to 2px minus p squared, right? And here what I'm going to do, let's multiply the 4p over to the right-hand side. So that's going to give me p minus 2x is equals to 8p squared times x minus 4p cubed. And if I rearrange, I'm looking at p plus 4p cubed is equals to 8p squared times x plus 2x. And if I factorize x out, okay, in fact, I can probably factorize the 2 out as well. So I've got 2x outside of 4p squared plus 1 is equals to, and then the p plus 4p cubed can be factorized into p outside of 1 plus 4p squared. And this tells me that the 1 plus 4p squared and the 4p squared plus 1 cancel from both sides, and therefore x is equals to p over 2. So if we know that x is equals to p over 2, right, so the x value of t is obviously going to change according to p. And what we can also say is when x is equals to p over 2, right, so when x equals to p over 2, remember the equation of the line, of the orange line. Now, it doesn't matter which equation we're working with. We can either take our x value, substitute it into the equation of the orange line, or we can substitute it into the tangent. Okay, it doesn't matter since t lies on both lines. But if I go with the orange line, we know that our y value is given by p minus 2x over 4p. So in other words, when x equals to p over 2, our corresponding y value is going to be p minus 2 times p over 2 divided by 4p, and that's going to give me y is equals to 0, right? Because I get p minus p divided by 4p, so that's going to be 0. So therefore, the coordinates for t is going to be p over 2 comma 0. Now, if I want to find the locus of t, right, the x value is p over 2, but the y value is always 0. So what this is saying is that no matter where p is, as p moves around on the parabola, the resulting interaction between this perpendicular line and the tangent is always going to get me this point which lies on the x-axis, or in other words, where y is equal to 0. And now the x value in this particular case doesn't really matter too much, right? X value just reflects that it is essentially half the distance between the y-axis and the point P, but the y value is always 0. So this tells us, okay, that the locus of t is the x-axis. Right? So the locus of t is the x-axis. So as p moves around, t is going to continue to move, but it will always lie somewhere on the x-axis. We don't know the x value. Okay, the x value is p over 2, which means that it depends on p. So it could be anywhere, right, on the x-axis, but it always lies on the x-axis, and that's the important part. So the locus of t is the x-axis, or in other words, y is equals to 0. And that's what we have for example 3.